But I'd like to introduce the next presentation, and I'd like to just first play for those who have, let me just ask, how many people have seen the original 23-minute NAWAPA tour, which goes through the project? Okay, so I want to, if you can just play at double speed, start from the very beginning. Go back, zoom out. Okay, this is the, here we can see, this is the northern part of the NAWAPA system called the collection function. The presentations we're going to be dealing with today are related to the transfer function of the NAWAPA system, at least the two I'm introducing right now. The collection system begins with these giant reservoirs which capture 15% of the 800 million feet runoff. There you see the Copper River Reservoir, which is connected through this 30-mile long Alaskan tunnel to form this giant Tanana Reservoir. Here we're still in Alaska. We cross over into the Yukon, which is a very big reservoir here called the Yukon Reservoir. You can see it fills up this whole region. And that collection of actually 4 billion acre feet storage, maybe not exactly that much just there, but it's large, is brought down the Yukon River into British Columbia, and down the Yukon River, actually, sorry, right here, Whitehorse, crosses the border here into British Columbia. So this whole collection is at 2,100 feet elevation, which is where it left the other system. And at 2,100 feet, it enters through Juneau Dam in Juneau, Alaska. We create a big dam that creates this Taku Reservoir. It's elevated now 300 feet at the Taku Lift. Now we go up to 2,400 feet. We're at 2,400 feet. The water level is all there at the Taku Lift. There's another contribution by the Mackenzie River Basin, but now we then flow across. We're going on the coastal mountains. We're placing dams so it doesn't all flow into the ocean, right? So we're continuing this flow along this, what's called Nass Reservoir. It's 500 miles long, roughly the whole winding it's a long thing, but this whole system here at 2,400 feet then enters a natural lake, Stewart Lake and Babine Lake. So we're still at 2,400 feet elevation, and this entire flow of water from the Mackenzie River Basin and the Yukon Basin and the Susitna Copper River watersheds is all carried along until we get to Prince George. A lot of it dumps down into Prince George there to go into the Fraser River, but 700-foot lift pumps a lot of the water into this Rocky Mountain Trench. And there it's going to require 6,800 megawatts to drive those pump lifts. This Rocky Mountain Trench is 500 miles long and dams the Columbia River, Fraser River, and another river. But we can see the Mica Dam there will have to be, which it exists, it will have to be increased by 300 feet to hold back this flow at 3,000 feet elevation. That's where we're at in the Rocky Mountain Trench. So this is a 500-mile long trench storing 520 million acre feet of water, which is an enormous quantity of water, and 72 million acre feet will be available from this trench per year for the states here. Canada gets its water not from the Rocky Mountain Trench, but up higher in that system, a branch off. So here the Rocky Mountain Trench Dam is the last dam in the Rocky Mountain Trench there. So now you can see kind of above. Here we're going to look at this transfer function now. The water flows out of the Rocky Mountain Trench into Montana for a very brief period of time into Flathead Lake. That's Montana. Big lake. We then create this big reservoir and Paradise Dam, which was supposed to have built in Idaho. Now, in Idaho, you can see here there's a series of orange lines. Those are tunnels connecting all the reservoirs. But each reservoir has a pump lift, and we can see those nuclear plants is where these pumping stations would be, and where we might drive them with nuclear power. All of these, what you just seen, is a 2,450-foot lift from 2,800 feet and Flathead Lake Clearwater Reservoir up to here, the Sawtooth Tunnel. You can pause it. That's the part I wanted you to play slower. That's fine. So that whole part there, there's a series of reservoirs, and it lifts each step. The largest lift is 700 feet. We can go through it again slowly before Terry speaks. But that system there, the Sawtooth Lift, is an inflection point and will probably be where we have a control room that monitors all the reservoirs of the entire system. And the people down in Mexico who will be receiving 20 feet of water will have to put their order of water to Canada or Alaska a number of months in advance for them to receive their water. Let's say if they were in Mexico and you wanted your water in August, you would have to place your order to the NAWAPA management system in what month? Just to guess.
Previous September.
January, yeah. That's what the Parsons report says. Now, it's not because water takes that long to flow down the earth, but that the whole reservoir system would require a certain amount of all management and all the needs of the system and all of that. So there's a general forecasting system that will have to be set up for this whole system, and it will also have to take into consideration weather, the reservoir levels 5 months from now, and what kind of effects we're going to have and who's going to need what. So that'll be itself, as I said before, a grand scale question. I want to introduce this Sawtooth Lift driven nuclear system, a presentation by Dr. Alan Salzberg,